This video is going to cover section 8.2, operations with matrices. It's still part of unit 8, which is matrices and determinants. Okay, so a few things here at the top for you to copy. The representation of matrices. So we saw a little bit of what these look like in 8.1. Then we're going to go a little more into detail on how to construct them and what they represent. Okay, so we can write a matrix using an uppercase letter such as A, B, or C to give it a name. So for example, we can say matrix A is all of this, okay? We can also use an enclosed element such as this that's in brackets. So we can also name it by this form as well. I'll go ahead and show you what ij mean in just a bit. And we can also do it as a rectangular array, which is what we did in 8.1, where you had those two like really big bracket looking things and a bunch of numbers in between. Okay. Um, two matrices. So let's say we call it A, or we can do it with the brackets of lowercase a with ij elements and B are equal when they have the same dimensions. Okay, so m by n and all corresponding entries are equal. So I mentioned that ij a little earlier, a few seconds ago. Basically, this would be kind of like your row. So in row 1 and column 2 or column 1. So we're always thinking row by column. M by N kind of, uh, you can kind of think of it as the same way as well when we're talking about which entry. So here we go. Equality of matrices, example 1. We're going to start off very slowly here. We are trying to solve for our A row 1, column 1 entry. Okay, get that a little bit better. Row 1, column 2. Remember, these are the rows. So this is row 1, this is row 2, this is column 1, this is column 2. You could think of it like that if that helps. Okay, but this is just kind of like on the side, so don't confuse it as part of the matrix. Um, this would be row 2, column 1, row 2, column 2. Okay, so we're saying that these two are equal. So all we have to do to find these values is match them up. So since this number 6 right here is part of row 1 and column 1, this would be the same as A11. So A11 is just 6. I mean, you can kind of tell which ones belong to each other. This one right here would be row 1, column 2. So we're thinking A12. And if you just look at it visually, okay, you can see that this one matches that one, this one matches that one, and so forth. Okay, so A21 is going to be row 2. Oh, I put a 1 there. That should be a 2. Row 2. Okay, this is the second row. Row 2, column 1. So row 2, column 1 is going to be -2 here. And last but not least, row 2, column 2 is the 4. So A subscript 2, 2 is 4. And that's it. We're just matching our elements. So which one corresponds to which entry? Okay, let's go ahead and look at something a little bit more complicated. So we have some more stuff to write at the top. Okay, we have the definition of matrix addition. So we can actually add matrices. So we're given a one array and another array if, let me see, we have kind of sort of the same dimensions. Okay, so if the dimensions are both n by n or whatever those numbers are, the sum of those matrices is going to be a plus b. So the two matrices where the entry in this position is added to the entry in the same position in the other matrix. So basically, the positions will correspond and we just add them up. Okay, and it does tell us here the sum of two matrices of different dimensions is undefined. So the dimensions do have to be the same. So this is super duper important right here. Okay, so let's look at a few examples. Again, this part won't take too long because these are this is just the beginning stuff. So hopefully you don't find it too difficult. To find the sum if possible. So before I even do that, I'm going to go ahead and define my dimensions. Remember that the dimensions are represented by m by n, and I think we saw this in 8.1 if I remember right, where this is the rows and this is the columns. So how many rows, how many columns, okay? This first one right here looks like it's two rows, so 1, 2. by 2 columns. So it's 2 by 2. This one is also 2 by 2, which means we can go ahead and add them. Okay, so what I'm going to do is I'm going to kind of use a little bit of algebra 1 methods here just to show you how to match these up. We're going to take our first entry, row 1, column 1, and that would be my 4, and match it with the row 1, column 1 here. So that would also be the whatever's in that first position. So for the first position right here, 4 plus 2 is 6. Okay, for row 2, column 1, my row 2, column 1 over here is this 0. So row 2 is going to be 2 plus 0, which is just 2. Okay, hopefully you're getting the idea here. Think of it like not like terms, but like positions, more like. Okay, so now we have row 1, column 1. Same thing over here, row 1, column 1. -1 plus -1 is -2. And you don't have to put these shapes, okay? I'm just kind of doing it for this first example just to kind of make the point here. And then we have the last position here. Let's do oh, I don't know. I'm just gonna do like a shading here. We'll do that. So this position, which is row 2, column 2, -3 plus 6 is +3. Okay, so this would be our resulting answer. This would be the sum. I'm going to write it a little bit more officially because we don't usually write matrices with shapes. So it'd be 6, 2, -2, and 3. And it's as simple as that. So we like matrix addition, and then works the same for subtraction. Okay, we'll do an example of that in a bit. Because all we have to do is add up the same positions. Okay, let's look at the next one. So for example letter B, I should say, we have let's see, 1, 2, 3. So 3 column by 1, 2. So 3 by 2 is the dimensions. For this one, we also have a 3 by 2. So we can go ahead and add these up. And we're going to do the same thing. So first position, 2 and -2 is 0. Okay, 3 and -3 is also 0. 0 and 0 is 0. Okay, -1 and 1 is also 0. 4 and -4 is 0. And -2 and 2 is 0. So our answer for this one is 0. And there's actually a special name for this one, which we'll see in just a bit. Okay. Last but not least, on this example, letter C, we have another set of matrices. This one's going to be 1, 2, 3. So 3 by 1, 2, 3. 3 by 3. This one is 2 by 3. So right here, since these two are different, I should have done like that. This one right here, to be specific. So those two, our M positions are different. Okay. That means that this is going to be undefined. We cannot add it together. Please note that this is undefined for the sum. For the sum. When it comes to multiplication, it's a little bit different. Okay, so we'll see that in just a bit as well. All right, let's move on. So far, hopefully it's nothing too bad. We have the definition of scalar multiplication. Okay, scalar multiplication is basically just multiplying the well, it could be multiple, but multiplying a matrix by one number, which is this little lowercase c, and we call it a scalar. So think of it kind of like a scale factor if you go back to geometry. Okay, so if A is this matrix, okay, with these terms inside, these elements, and we have it's this n by n matrix, and C is a scalar, then the scalar multiple of A by C is basically C times everything that's in that matrix. So all the elements of this matrix are going to be multiplied by C. So there's a special little note here that says negative A represents the negation of A. So think of the negative in front as a scalar of -1. This is the same thing. Okay, so if we do have something that's the same dimension and we have it in the sense of subtraction, like A minus B, the same rules that apply for addition are going to apply for this guy. Basically, A minus B is the same as A plus -1 times B. So we can think of it like that as well. okay? Let's go ahead and do an example that has something like this. It says for the matrices below, find A, which is this guy minus this guy, and B, which is 3 times this one minus 2 times this one. So let's do letter A first, okay? Letter A is just A minus B. So basically I'm going to have 4, 0, I'm just copying this right now. -3, -1, 4, 8, okay? Minus, or you could think of it as plus, if you want to do the -1, -1 times all of this. So 0, -1, 1, 4, 3, and 7. And I forgot to mention, but these are both the same dimensions. They're both, let's see, 3 by 2, 3 by 2. So we can go ahead and perform the operation, okay? So the first thing I'd want to do for something like this, if you're going step by step, is to fix this one. So that -1, think of it like order of operations, right? You would distribute to all the numbers inside. Okay, so this right here, I'm going to rewrite this a little bit, is going to be, I'm going to put it on this side. Let's see, -1 times 0 is still 0. -1 times -1 is 1. -1 times 1 is -1. -1 times 4, -4. -1 times 3, -3. And -1 times 7, -7. So this guy right here is the same as what I just did right here, okay? And I'm just going to copy this one over. So 4, 0, -3, -1, 4, 8. And I realize that you can probably do this, a little bit faster, but that's okay. This is just notes. We're going step by step. Okay, so basically all of my numbers in here just became the opposite. Okay, opposite sign. Now from here we can go ahead and add these up. So this is going to give us, let's see if I can get this to fit here. I should have done this a lot smaller. 4 plus 0 is 4. 0 plus 1 is 1. -3 plus -1 is -4. All squished in there, okay? And then the second column, -1 and -4 is -5. 4 and -3 is 1. 8 and -7 is 1. So this right here is my answer. It's all squished over here, but this is the answer for part A. Okay. If we wanted to do this but using subtraction, we could have done the same thing. So 4 minus 0 is still 4. 0 minus -1, okay, is the same +1. -3 minus 1 is -4. -1 minus 4, okay, is -5. 4 minus 3 is 1, and then 8 minus 7 is 1. So same thing. Let's look at part B. Part B is asking us to do 3 times A minus 2 times B. So now we're going to do 3 times the A, which is going to be, again, all this, 4, 0, -3, -1, 4, 8. I'm just recopying matrix A, okay? Minus, I'm going to keep the minus this time, 2 times B, which is all of this right here. So 0, 4, -1, 3, 1, 7. Okay, so you can either go ahead and do the multiplication of -2 and do it that way, or we can also think of it as plus -2 like this. Okay, so let's go ahead and do this part first. So 3 times all of this is going to be 3 distributed into everything, basically. Okay, so that's going to be 3 times 4 is 12, 3 times 0 is 0, 3 times -3, let me move this down a little bit, 3 times -3 is -9, okay, 3 times -1 is -3, 3 times 4 is 12, and 3 times 8 is 24. So that represents the scalar of 3 being multiplied here in matrix A, minus 2 times all of this. So we're going to use the minus this time, see how that works. So 2 times 0 is still 0. 2 times 4 is 8. 2 times -1 is -2. 2 times 3 is 6. 2 times 1 is 2, and 2 times 7 is 14. Hopefully I didn't go too fast here, okay? So if we go ahead and stick with the minus, we're just gonna subtract, okay? So now we're looking at 12 minus 0. All right, so 12 minus 0 is 12. 0 minus negative 2 is like saying 0 plus 2, so that's going to be 2. Negative 9 minus 2 is negative 11. Okay. Negative 3 minus 8 is negative 11. 12 minus 6 is positive 6. And then 24 minus 14 is 10. Okay. And this should be our answer. Go ahead and check the math. Make sure it works. Moving on. So now we have some properties of matrix addition and scalar multiplication, which is what we just kind of saw right now. So here we have all our commutative, associative, and distributive properties, as well as the scalar identity, which we're going to talk about in a little bit. Basically, we can swap them and it'll still come out the same. So A plus B is still the same as B plus A. That's the commutative property. Associative means that if we have them inside some sort of parentheses and we move those parentheses, it's still going to be the same thing. Same thing with multiplication. The order of the multiplication with a scalar does not matter. So if we had like 3 times 2 times the matrix, that's the same as 3 times the matrix times 2. If that makes any sense. And then we have our identity scalar, which we'll talk about later on. I believe it's on the next page. There is this special matrix called the identity matrix. And basically, whenever you multiply by this one, it gives you the exact same answer. Kind of like 1, multiplying by 1. Okay. And then we have the distributive property, which is pretty self-explanatory. This is the same as that, and that is the same as that. Let's go ahead and evaluate one more example like this. This is one of the some of the properties being put together. We have 2 times a matrix plus another matrix. So we're going to use our distributive property to multiply this out. Okay. Where did I leave? There we go. So I would multiply the 2 here and the 2 here. So we're actually looking at 2 times all of the first matrix, okay, plus 2 times the second matrix. Okay, so there's our distributive property in use. And then we're just going to go ahead and, multiply everything times 2 and then add it up. So from here we have, we'll do it this way, 2 times, let's see, 2 times 1 is 2, 2 times negative 2 is negative 4, 2 times 3 is 6, and 2 times 2 is 4. Please make sure if I make a mistake, let me know. I am going a little bit fast because this is a pretty long subunit, okay? So I tend to make mistakes that way. So hopefully I don't make any. Next part, plus 2 times negative 4 is negative 8. 2 times negative 3 is negative 6. 2 times 0 is 0. And 2 times 1 is 2. So we are left with these two matrices at the bottom, okay? And just like before, we can go ahead and just add up the corresponding elements. So row 1, column 1, 2 plus negative 8 is negative 6. Row 2, column 1, negative 4 plus negative 6 is negative 10, okay? 6 plus 0 is positive 6, and then 4 plus 2 is 6. And this would be our final answer for this one, assuming I did everything correctly, okay? All right, so that's basically it, guys, for properties of addition, and I guess you could think of it subtraction if you think of a negation as, not negative. So let's go ahead and do one more example here, and then we're going to probably cut this video in half. So we have example 5, where we're solving a matrix equation, okay? So when we're solving an equation, usually our capital letters will represent a matrix of some sort. In this case, we're solving for x. So if 2x minus a equals b, well, how do we solve for x when a and b are matrices? What we're going to do is we're actually going to solve this guy here. for x first. So I'm going to solve this first. So we're going to solve first for x, capital X. We use the capital letters for matrices. Okay. And then once I know what x is equal to, I can use my operations here with matrices to figure out what the x matrix is going to look like. So here we go. This should be kind of an easy part in the beginning. 2 times x minus a equals b. Okay. Well, if I'm solving this, I would add a to both sides like such, which gives me 2x equals b plus a, or a plus b, however you want to do it. You can use your commutative property there. And then we're going to divide both sides by 2. So x, capital X, which is a matrix of some sort, is equal to b plus a over 2. But since we're not used to dividing matrices, what I'm going to do is I'm going to pull that 2 out and turn it into a 1/2. So it looks like this. And now this is a scalar of 1/2. So here you can think of it like a little c is equal to 1/2, where you're multiplying these guys by 1/2. Okay, so for this one, I'm going to go ahead and solve it a little bit different from the previous example. I'm going to actually, we could distribute the 1/2 and then add it. I'm going to add it first and then do the 1/2 just because I don't want to deal with the 1/2 since it's a fraction. Same rules apply. Let's go ahead and do that over here. We're doing this now, 1/2 b plus a. So 1/2 matrix B, so 4, -2, 1, -1, and 5. So there's my matrix B, okay? Make sure it matches, plus letter A. So my matrix A is 6, 0, 1, and 3. And this time I'm going to use the other method, the kind of going backwards here. I'm going to add these two up and then do the 1/2 because you're allowed to do that as well. So this would be the same as 1/2, and then I'm going to start adding these two things together. Okay, so 4 plus 6 is 10. Let's color code a little bit. So these two give me 10. -2 and 0 is still -2. -1 and 1 is 0. And then 5 and 3 is 8. Okay, so this is the matrix I get when I add these two up. Now I'm going to go ahead and distribute my 1/2 to everything in here. So I'm going to distribute 1/2 here, 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 and here, which is going to give me 1/2 of 10. 1/2 times 10 is going to be 5. Think of it like, what is half of 10? Okay, this is a big bracket for a matrix. Half of -2 is -1. Half of 0 is still 0. And half of 8 is just 4. And this is my answer right here. So this means that my x, capital X, is equal to all of this matrix. 5, -1, 0, and 4. And if you wanted to check this, because just like most equations, we could check this, okay? Well, you would plug all this back into what we got up here. So 2 times this should give me something, and if I subtract A, I should get B, okay? We're not gonna go through that because of the time, but basically it's the same as just plugging numbers back in, okay? The last thing we're gonna do is go over this thing at the bottom here that's called the zero matrix, which we kind of sort of saw in I think the first example or so. And the first or second example, the zero matrix is basically a bunch of zeros. Okay, so we can write it as an n by n matrix, and it has nothing but zeros. So for example, the zero matrix here of a 3 by 3 would be 3 by 3 and a bunch of zeros. 2 by 2 would just be 2 and 2, and again a bunch of zeros. And that's basically it, guys. Okay, so I'm going to go ahead and cut the video short here, and we will continue the next part of this of 8.2 in the second video. Thanks.